So let's consider another configuration of charge. Let's say that we have a little narrow cylinder and it's embedded inside of a spherical shell. Okay, so the little inner cylinder has radius, let's call this radius A, and the outer one has radius B. All right. And so we can say, for example, that we put a positive charge on the inner one and equal negative charge out here. So what's going to happen is the electric field is going to be doing that. Okay. And so I want to find the capacitance here. Why is there a capacitance? Well, because same situation here is that we've got positive and negative charge, which means if we connect them, current's going to flow from one to the other, and so it's going to release energy. And so again, this will act like a capacitor. And so to find the capacitance, we know that capacitance is defined to be Q over V. And so we need to have these terms. Okay. So when we look at it and say, well, this is straightforward. Okay. Q, we're going to know that Q is going to be lambda times L, where L is the length of our device. So what about the V? Well, if we look at it on the end, we've got this little thing right here of A and then B, and the electric field does like this. I'm just, so what we've got here is, this thing here. I've now put my eye right here looking down it. Okay, so we know that the electric field goes out that way. So we know that the electric potential is minus integral E dot ds. Okay, and so what we've got here is basically the integral from A to B of E dot ds. So that's lambda over 2 pi epsilon naught over r dr. Okay, and so we can do the integral here. This is minus lambda over 2 pi epsilon naught integral A to B of dr over r. So that's going to be equal to minus lambda over 2 pi epsilon naught natural log of B over A. Okay. Now, that's going to be this. So what we do is we look at it and say, well, we want to take absolute value of that, because that's going to be the decrease in energy from there to there. So we want to know the absolute value of the voltage. So the absolute value of that voltage there is going to be equal to lambda over 2 pi epsilon naught natural log B over A, because we're just interested in the difference in the voltage, okay, between the inner and the outer. Okay, so now to find the capacitance, which is Q over V, this is going to be equal to lambda L divided by lambda over 2 pi epsilon naught natural log B over A. So in other words, this is going to be equal to 2 pi epsilon naught times L divided by natural log of B over A. Notice that the amount of charge or anything that's there is all gone. All that's left is just the geometry of the system. And so L is the length of it, and then the natural log of the ratio of the inner and outer, the natural log of the radius of the outer shell to the inner conductor. Well, where have you seen something like this, where you have this long little cylinder here inside of a spherical shell? That's coaxial cable. Okay, so we have a piece of coax cable right here, and so it's actually got some capacitance. Now the capacitance here of the cable is 2 pi epsilon naught L over natural log B over A, which means the longer the cable is, the more the capacitance it has. Now that actually matters because what happens is that you end up with having issues with electrical circuits, AC circuits, for example. Capacitance is an active part of an AC circuit, and so it's an active circuit element. And so if your coax cable has capacitance, that can affect the circuit. And so if you actually go buy coax cable in bulk, it comes in a reel, and the reel actually lists the capacitance per length. And so it'll say capacitance is like so many picofarads per meter, or per foot or whatever. And so that's actually a known quantity and something that is an issue using coax cable.